Hello, everyone. Welcome to the HPL seminar this week. Today, it is my great pleasure to introduce our speaker, Dr. Venus Joumaa. In 2000, Venus received a Bachelor's of Science degree in biochemistry at the Lebanese University in Lebanon. And then she moved to France and started her master's work in biomechanics and biomedical engineering at the University of Technology of Compiègne. After she achieved her master's degree in 2001, Venus decided to continue building up her academic career by doing PhD work at the same university under the supervision of Dr. Francis Goebel and Dr. Ola Alaf. Her research was focused on how the stem cells in skeletal muscle would be affected by overload induced by tail suspension, and also how single muscle fiber would adapt to the changed loading environment. After she received a PhD degree in 2005, she came here at the University of Calgary as a postdoc, working with Dr. Walter Herzog, and then she became an adjunct assistant professor in kinesiology in 2009. Since then, Venus has been primarily working on understanding the structural, functional, and metabolic properties of skeletal muscle and cardiac muscle as well at the two different levels, molecular and cellular levels. Aside from her academic career, when I asked her about any interesting facts about herself, she wanted to share a brief story with us. So when Venus was 6 or 7 years old, her teacher named his daughter after Venus, but then Venus did not seem to remember this for a long time. And then about 20 years later, when Venus was giving a lecture at a university in Lebanon, a student came to her and said that her sister was named after Venus, and that was how she got reminded of this story. After that, Venus wanted to keep in touch with the students and her family, and also the younger Venus as well. But unfortunately, she lost contact with them, which is kind of sad. But who knows if the students, or who would not be a student anymore right now, watches the HPL seminar recorded and posted to our website, and she might contact you again. Today, Venus will be giving a talk, which is about X-ray diffraction patterns of skeletal muscle, a peek at the structure of sarcomeres after active stretch and shortening. Whenever you're ready, Venus.
So do you see my screen all right?
Yep, I see your screen and I hear you well.
Okay, perfect. Oops. So today I would like to share with you the experiments that we did at the Argonne National Laboratory. So the ANL is a very high-tech lab operated by the University of Chicago for the US Department of Energy. It's located in Lemont, which is about 60 kilometers southwest of Chicago. So the ANL houses many research labs and facilities. And among these facilities is the Synchrotron light source. So I have in this image some of the buildings at the ANL and the Synchrotron ring in the middle here. So the inner part of this ring is called the storage ring, like the inner part here. And then the outer part of the ring is formed by the different research labs. So a synchrotron is basically an electron accelerator. So the electrons are accelerated to nearly the speed of the light. Then, through different physical processes, mainly bending, they emit very high energy and very bright light that is about 1 million times brighter than the sunlight. And so this light is created and stored in this storing or in this storage ring. And then it is divided or it's segmented into X-ray beams, and each beam is diverted, each beam based on its wavelength and its energy, it's diverted towards one of these slabs that are surrounding the storage ring. And so this is a schematic of this ring again. So the labs that are around it are 35 labs, numbered from 1 all the way to 35. And so as I said, each lab receives, so if we could say receive a beam, an X-ray beam, depending on the applications in these labs. These applications varies between looking at solid crystals to looking at biological materials. So the beam line that we are interested in and that is able to give us like the resolution to look at skeletal muscle is beam line 18, operated by our collaborator, Dr. Tim Irvin. So this is the inside of this synchrotron ring. So on the left-hand side, we have the wet labs in which we prepare solutions, we prepare the samples before our X-ray experiments. And on the right-hand side, we have the experimental chambers. So in which we have the X-ray going through our samples. So these experimental chambers are called hutches. So these hutches are very well protected. When the X-ray is on, no human presence obviously is allowed inside. And so here I'm going to show you a video of the hutch and a search for a human presence before we are allowed to turn the X-ray on.
Searching station D. Exit immediately. Searching station D. Exit.
So it says searching station D, exit immediately.
Searching station D. Exit immediately. Searching station D. Exit.
And so if there is no human presence, the door is locked and we are allowed to turn the X-ray on, and we control our experiments inside the hutch from outside, from computers outside. So how do we get beam time at the ANL? So usually we write a research proposal and we apply for beam time by the deadline. And if we are lucky, we are allocated what we call beam time by our specific beam line. And so we are lucky to have been allocated beam time at beam line 18. And so the beam time was 96 hours of continuous / non-stop work. And so once we're ready to do the experiments, we were staying on site at the ANL at the guest house, and we divided our cells into teams to work in shifts to perform these non-stop experiments. So it's to note here that we have in Canada a synchrotron. It's in Saskatoon at the Canadian Light Source. However, it's not available. So the beam line required to look at the structure of the muscle is still not available at Saskatoon. So what is the research that required us to do these X-ray experiments? So we are interested in the structure of the contractile proteins after active stretch and shortening. So to give you a background, so this is the force produced by a muscle if we activated it at this length, and then we do an active shortening and we wait until steady state is reached. So the force at the end here is lower than the purely isometric contraction performed at the final muscle length. So the length at the end here is the same between the active shortening and the purely isometric contraction And in both cases, we have isometric contractions, but the force after active shortening is lower than the purely isometric contraction. So we have the same thing after active stretching. So the force, the same thing in terms of difference in force. So after active stretching, we get, so if we activate the muscle at a short length, then actively stretch it to a final length, we get this force when all transient are gone. So this force is always higher than the purely isometric contraction performed at the final length. So again, the length of the muscle is the same in these two states, but the force after active stretch is higher than the purely isometric contraction. So these force enhancement and force depression have been observed in all experimental preparations, starting from in vivo human muscles to single myofibrils and single sarcomeres. So why are they important and why are we interested in these properties? So basically, because they do not agree with our current understanding of muscle contraction based on the cross-bridge theory and its derivative, the force-length relationship. So this is the force-length relationship. So we have here the normalized maximal force in function of sarcomere length. And so as you can see, according to this relationship, the force produced by a muscle depends on its length, because it depends on the amount of overlap between actin and myosin. And so for a given length / for a given amount of overlap, we should have one force and only one. However, after active stretch and shortening, so here I'm showing the normalized force again in function of sarcomere lengths. This is a purely isometric contraction. And so after active shortening and stretching, we could have an infinite number of forces for a given length, depending on how we play around with our experiments. So what's the origin of these force enhancement and force depression? So there have been many theories suggested to explain that. However, none of these theories, except for one, the stress-induced inhibition of cross bridges, but in a very theoretical way. So none of these theories has touched on the structure of the contractile filaments and the contractile proteins after active stretch and active shortening. So this is the sarcomere, or a schematic of a sarcomere. So this is the Z disc. This is myosin in the middle, or the thick filament formed of myosin in the middle, and the thin filaments formed of actin. And so the force produced by a muscle is produced when these myosin heads interact with actin, do their cycle, rotate, and so produce force to bring the myosin, to pull the actin towards the center of the sarcomere. So there is a possibility that in order to have an increase in force, we could have an increase in the proportion of these cross bridges that are attaching to actin. And when we have force depression, we could have a decrease in the proportion of attached cross bridges. Another mechanism could be that there is a change, or there are changes in lattice spacing after active stretching and shortening. So lattice spacing is the spacing between the filaments. Let's say the spacing here between myosin and actin. So for the cross bridge to interact with actin, so it needs to attach first, and then it needs to rotate. So if the lattice spacing is getting larger or smaller, the cross bridge may have an increased or decreased possibility to attach. Also, if the spacing changes, so there might be a change in the force produced per cross bridge. So here I have again a zoom in schematic of an interaction between a cross bridge and an actin filament. So this is the cross bridge, this is the actin filament. And so a cross bridge produces force when its spring-like structure here is stretched. So if the lattice spacing is different or it changes after active stretching and shortening, this spring would be stretched to a different extent, and so the force produced per cross bridge would be different. And so these could be two possibilities for a change in the force. And so how are we going to test these possibilities? So X-ray has given a wealth of information about the structure of proteins and the structures of like materials in general. So I'm not sure if you remember that the DNA was first of the 3D structure of DNA was first suggested by Watson and Crick in 1953. But I'm sure it's much less known that this model was the result, or in part was the result of the X-ray diffractions patterns provided by Rosalind Franklin to Watson and Crick. Similarly, so Hugh Huxley did very interesting work before the suggestion of the sliding filament theory. So he did X-ray experiments on muscle in order to determine the structure of the filaments, which led later to the suggestion by him and by Andrew Huxley and collaborators of the sliding filament theory. So another thing that X-ray diffraction allows us to do is that it allows us to test the muscle, in our case, in its physiological conditions. So we could test the muscle at rest, in regular state, activation, after stretch, after shortening. And this is actually what Hugh Huxley did in 1953. And so this will lead me to the purpose of this study, which is to determine, using small angle X-ray diffraction, the effect of active shortening and stretching on lattice spacing and the proximity of cross bridges, the proximity of myosin heads to the thin filaments in skin muscle bundles. So I would like to give you a very quick overview of the X-ray diffraction in skeletal muscle, especially the equatorial reflections. So when an X-ray beam passes through a skeletal muscle, it gives an X-ray diffraction pattern, which is like what is shown here. However, for the sake of this presentation, I'm not going to talk about the meridional reflections. I'm going to talk about the equatorial reflections only, which are these reflections here. But I'm looking at them with lower like brightness of the image, so they are here. So these equatorial reflections, they result from diffractions in the equatorial plane, or along the equatorial axis, which is perpendicular to the length of the muscle. So in other words, we're getting the reflections from the cross-section of the muscle. So what do these reflections tell us? So they can determine the lattice spacing inside the muscle, and they can tell us about the proximity of cross bridges to actin. In other words, the proportion of attached cross bridges in the muscle. So how does this happen? How does it do that? So in materials, like basically in solid crystals, when atoms are arranged very nicely in an ordered way along, let's say, two planes, this plane and this plane, parallel planes separated by a distance d, if we shine an X-ray beam through this material, and this material is able to diffract the X-ray beam, the diffraction pattern here and the distances of the diffraction dots will allow us to determine very accurately the lattice spacing between the plane D from Bragg's law and from applying some trigonometry on our setting. And so we get this diffraction. So from this distance here, measured from the center, we could get D. So in the muscle, do we have this nicely ordered structure? Of course we do. So this is our sarcomere, again, myosin and actin. And imagine that we are looking at the sarcomere from this side. So what we see is the myosin filament in the middle, and it's surrounded by 6 actin filaments. And so if we do a cross-section in the middle here, in the middle of the A band, we will see this nice hexagon, like the 6 myosin in the middle and 6 actin surrounding it, lattice spacing. So if we look closely, so these are the myosin molecules, the big circles, and these are the actin molecules, or the filaments rather, these small circles, small dots. And so we see that myosin are very nicely arranged in a plane here, and then another set of myosin in another plane. And these planes are separated by a constant distance. And so these planes are called the 1, 0 planes, and this distance is D10. And so if we shine a beam, an X-ray beam through the muscle, we will get very nice diffractions of this 1, 0 planes, and we could, based on Bragg's law, determine D10 from the distances in our X-ray patterns. So now one mission is accomplished. We have the lattice. We could have the lattice spacing from the equatorial reflections. How about the proximity of cross bridges? So we come back to our myosin filaments here and the myosin plane. And so think about, please, the myosin heads here. So these myosin heads in a resting muscle before activation, they are very close to the backbone of myosin. So before that, I need to mention that, so from the X-ray, there are 2 parameters that we need to think about. So the first one is the distances of the reflections, and the other one is the mass of the material being or the material that having the X-ray passing through. So the distances in the X-ray patterns, and the other parameters is the intensities of the dots on the X-ray pattern. So the intensity are the results of the amount of mass in the X-ray beam. So if I have a big muscle and I have a small muscle and I pass a beam through them, the big muscle is going to give me a much stronger, in terms of intensity, much stronger peaks compared to the small muscle. And so based on this, I come back to my myosin heads. So the myosin heads in a resting muscle, they are very close to the myosin backbone. And so in other words, they are located in this myosin plane. Now, what happens when the muscle is activated? So when the muscle is activated, as we know, the myosin heads are going to move away from the myosin backbone and go to try to attach to actin or attach to actin and rotate. And so they move away from this myosin plane towards a plane another plane that has actin in it. And this other plane is the plane 1, 1. And this plane 1, 1, we also see it on our diffraction pattern. And so in order to determine the proximity of cross bridges to actin / the proportion of attached cross bridges, we would determine the intensities of the reflections of planes 1, 1 and planes 1, 0. And so usually we do not express these intensities as absolute values, but rather as a ratio between 1, 1. So ratio of I11, intensity 1, 1 to intensity 1, 0. And so when we have an increase in this intensity, this means that there is an increase in the proximity of cross bridges to actin. So this means that there is a shift of mass from myosin towards actin. So this means that there is an increase in the proportion of attached cross bridges. And the opposite is correct. If there is a decrease in this ratio, there is a decrease in the shift of mass from myosin to actin, a decrease in the proximity of cross bridges to actin, and so a decrease in the proportion of attached cross bridges. And so using the equatorial reflection, we would be able to determine lattice spacing and the proximity of cross bridges to actin. So what experiments did we do? So we did our experiments in samples isolated from rabbit psoas muscle. So these samples were skinned for 2 weeks, and then they were mounted on they were shipped to Argonne, and they were mounted on a rig there between a force transducer and a length controller. So this force transducer and length control, so the whole system would slide towards, like it's in the hutch, and it would slide. It was sitting on a cart, so it would slide towards the center here, where the X-ray is coming from this tube, and then so the sample would be here, and then the diffracted X-ray would go into this tube towards a detector down here. So which is, so again, so everything is here, the sample is here, the X-ray shines through the sample, and then the diffracted X-ray will go all the way down to the detector that is located at about 3 meters down from the sample. And so the experiments that were done are active shortening experiments and active stretching. So the active shortening experiments, we did an activation, a purely isometric activation. We called it the reference contraction at a sarcomere length of 2.6. For the active shortening, we did the activation at a sarcomere length of 3. Then we did an active shortening to a sarcomere length of 2.6. And then at steady state, we exposed our sample to X-ray. And after exposure to X-ray, we did the stiffness test. So the stiffness is another way to have an idea of the proportion of attached cross bridges, because stiffness is just a quick stretch release cycle of the muscle. And the structural elements that respond to this quick stretch release are many. So we cannot say that this comes only from cross bridges. So for the active stretching experiments, we did our reference contraction at a sarcomere length of 3, and our active shortening was the active stretching. So we did the activation at 2.6, and then we did the active shortening. We waited until steady state, and then at steady state, we exposed the sample to, or the samples to X-ray, and then we did the stiffness test again, just to have an idea for the stiffness test, because it is what's usually performed in order to have the proportion of attached cross bridges. So because of the X-ray is very damaging to the structures, so this is an image of the, so actually it's a video. So this is our sample in the middle of the force transducer and the length controller. And the cross here is the beam, is where the beam will hit. And so because the beam is very strong, very high energy, and it might damage the muscle if it hits it just at one side. So what we usually do is we allow the sample to oscillate. So we call this the toaster, in order for the beam to hit the sample at different locations. And so we're not damaging the muscle sample just at one location. We are distributing the heat, so the damage would be less. So our outcome measures are from the mechanical data, force depression, force enhancement, and stiffness for after active stretching, and stiffness after active shortening. And our X-ray outcome measures are the D1, the lattice spacing 1, 0, and the ratio of intensities of planes 1, 1, 1 to the intensity of plane 1, 0. And so I think now we can suggest some hypotheses, since we know our outcome measures. So for force depression, we expect to see force depression and stiffness depression. We expect an increase in the lattice spacing and a decrease in the ratio, in the intensity ratio. For force enhancement, we expect to see force enhancement, but no change in stiffness, because this is what has been shown previously. And we expect a change, a decrease in lattice spacing, and an increase or no change in the intensity ratio. So what about the results? So for the force depression and stiffness depression, yes, we did see both force depression and stiffness depression. So this is the amount of depression. So it's the absolute depression. That's why it's not negative. So depression in force and depression in stiffness, which is about the same magnitude, like both of them, force and stiffness. Lattice spacing in the force depressed state. So this is the lattice spacing in the reference and the lattice spacing in the active shortening. And as you can see, there is no difference in lattice spacing between the state. So despite the fact that force is reduced after active shortening compared to the reference. And so it has been like believed that when you have a decrease in force, the lattice spacing should increase, because active force produced by the muscle produces radial force that affect the spacing. So if it's high, it's going to compress. If it's less in a condition compared to other, you will have an increase in lattice spacing. However, this is not what we saw. And I don't know why, but maybe it's because we have already skinned fibers, and lattice spacing in skinned fibers is already expanded. So maybe there is no way for the lattice spacing to increase more and still allow cross bridges to attach. Or maybe this force, depending on the orientation, it may not produce, like the force may, the effect of the radial component of the force may not be as high in this specific situation after force depression. So the other thing is the intensity ratio. So this is the intensity ratio in the reference condition and after active shortening. And as we can see, and as we hypothesized, there is a decrease in the intensity ratio, which means that there is a decrease in the shift of mass from myosin towards actin. And so, which means there is a decrease in the proportion of attached cross bridges after active shortening compared to the reference contraction. And so in the force depressed state, we could say that there is a reduction in the proportion of attached cross bridges. And so what is the mechanism that could be suggested for this reduction in the proportion of attached cross bridges? So I think that we have provided some experimental evidence to support the stress-induced inhibition of cross bridge theory, suggested by Maréchal and Plagge in 1979. So what this hypothesis states is that, so this is the sarcomere in a purely isometric reference contraction. And so this is the amount of overlap here. And now this is a sarcomere before active shortening, and this is a sarcomere after active shortening. So before active shortening, because the sarcomere length on the descending limb is longer, so the amount of overlap is smaller than the amount of overlap in the reference state. This is pretty acceptable. This is known. And so when we do an active shortening, there is an actin, there is a part of actin that is entering the overlap zone. And so according to Maréchal and Plagge, this actin filament, or these actin filaments, are strained by the force, the already producing the muscle that is already producing force, and this causes a rotation in the actin filament, which decreases the possibility for the cross bridges to attach. And so we think that we have provided some support for this hypothesis, however, not directly in terms of strain on the thin filaments, because we have not tested thin filament. I mean, based on what I have presented, but we have already tested thin filaments, but results are for future presentations. Keep the suspense. So results for force enhancement. So we saw force enhancement. So again, this is the enhancement of force and stiffness. So we saw an increase in force after active stretch, but we did not see a change in stiffness or an increase in stiffness, which is expected. This has been shown before. So in terms of lattice spacing, so here because the force is higher after active stretching, we expected a decrease in lattice spacing because of the radial force being higher after active stretching compared to the purely isometric reference contraction. And this is actually what we saw. So this is the lattice spacing in function for the reference and active stretch. And so as you can see, there is a decrease in lattice spacing. And this might be because, as I said, because of the increase in force. And so it's creating a higher compressive component. So for the intensity ratio, so there is no change in the intensity ratio between the reference and the active states. So this means that there is no change in the shift of mass between from myosin towards actin, and so there is likely no change in the proportion of attached cross bridges between the reference and the active stretch state. And this agrees basically with our stiffness results that also did not show any change in the proportion of attached cross or any change in stiffness. And so for the force enhanced state, we think that there is no change in the proportion of attached cross bridges. For the conformation of cross bridges, so there is a change in lattice spacing. So the conformation of cross bridges might be different between the states. But again, we do not have a direct measurement now to say that, yes, we have. So there is a change in lattice spacing, but not a measurement of the structure of cross bridges and of the conformation of cross bridges. So based on this, and basically based on the absence of a change in the proportion of attached cross bridges, we could say that in terms of mechanism, we cannot have a 100% like answer, or we cannot have 100%, but we cannot suggest a mechanism so far. But based on what we have been suggested in the literature, it seems that an engagement of a passive element is gaining ground here because the cross bridges are not changing. The number of cross bridges are not changing. And so in conclusion, we could say that for force depression, we have provided strong evidence for a decrease in the proportion of attached cross bridges after active shortening. And we have provided evidence to support the stress-induced inhibition of cross bridges, but not directly on the conformation of the thin filaments. For force enhancement, we could say that we have provided strong evidence for the absence of a change in the proportion of attached cross bridges, but a change in cross bridge conformation is still a possibility. But its contribution to force enhancement may not be as large, based on some meridional reflection experiments that we did later at Argonne, and they are again for future presentations. And so I would like at the end to thank Dr. Walter Herzog for his continuous support, and also for his excitement for these X-ray experiments and for his encouragement during these 96 non-stop experiments at Argonne. I would like to thank the X-ray team, Dr. Tim Leonard, Dr. Ian Smith, and Dr. Atsuki Fukutami. And I would like to thank the people at Argonne, Dr. Tom Irvin and Wei Kang Ma. And also I would like to thank our funding sources and thank you for your attention. And thanks a lot.
Thank you very much, Venus, for the great talk. So I would like to, before we get to the discussion period, I would like to kindly encourage you, everyone, to turn on your camera during the discussion period if you feel okay with it. And I think it'll give us some more active discussion period. Thank you very much for doing that. So if you have any questions for Venus, please use the icon raise hand button. So you can find the button when you go click reaction icon at the bottom of your Zoom screen. Also, if your Zoom does not show you the button there, please feel free to send me a message via Zoom chat, then I'll call on you when it's your turn. Now the floor is open for the question. Yes, Tim, please go ahead.
Yeah, Venus, thanks for the interesting talk. I was just curious. I think that a lot of people assume that volume is preserved during muscle contraction. But here you're suggesting that it's actually not preserved. Is that true? Is that a correct interpretation?
Why do you say that?
Because you hypothesized a difference in lattice spacing at the same length. And I assume that that difference in lattice spacing means a difference in muscle thickness or like the radial direction of the muscle.
Okay, you're right. So you're right, the muscle volume is preserved at, but in skinned fibers, that's another story. So some studies have shown that the volume is preserved, but most studies showed that it is not. So at the same sarcomere lengths, you might have different spacing because of the membrane is not there. So it may not be preserved. And at least from our experiments, it seems, I think we need to do a little bit more experiments to confirm that, but because we have the same sarcomere length and the lattice spacing is different, so we could also confirm that it's not preserved.
Okay.
In skinned fibers, at least.
Okay.
I see, Kun, you have also a question for Venus?
Yes. Thank you, Venus. That was really an incredible talk. Super cool work. Okay, my question. So if I noted this down correctly, it seems that for shortening, okay, you observe that the proportion of attached cross bridges goes down, and the stiffness of the muscle remained equal. And for stretch contractions, you observe that the proportion of attached cross bridges remained equal, and the stiffness also remained equal. Is this? I just tried to scribble it down quickly during your talk. Is that correct?
So correct for the stretch, but not very accurate for the shortening, because for the shortening, we saw a decrease in stiffness and a decrease in the proportion in the intensity ratio. So in the proportion of attached cross bridges.
Oh, okay. That makes my question obsolete. So I thought that those two were inconsistent, but then I noted that wrongly. Okay, thanks.
Yeah, so if they were not consistent, I would say that I would believe the X-ray diffraction more than the stiffness, because there are many other parameters, many other structural elements in the muscle that contribute to stiffness. So you might be right to wonder why they might be different, but yes. So stiffness, the X-ray is a more accurate measurement, I would say, of the cross bridges.
Okay, and what is actually, I'm not sure if maybe I missed that, but why is this proximity related to the proportion of attached cross bridges?
So the myosin heads are leaving the myosin plane and they are going towards the actin plane. And so I cannot say that they are attached, but I would say that they are getting close to myosin. So there is a very high possibility that they are attached cross bridges.
I see. But that is currently a hypothesis, let's say, or is there direct evidence for this? Okay.
So according to what people have done, so they say, that's why I was very careful, and people have been careful to say that's a shift of mass. So we are measuring a shift of mass, but we are interpreting it as a change in the proportion of attached cross bridges.
I see. Okay. Exactly. Okay. Thanks.
Yes, Art, please go ahead.
I guess I had a question, but I'm going to, it's sort of a brief question before that, which is related to Kuhn's question, which is, I'm wondering why we expect the myosin to have a different sort of home position. So let's pretend that they're not attached. So then I would expect that, you know, you're saying they should be close to the myosin plane. I have no idea where they should be, but I just expect that if you have cross bridges that are sort of buffeted by Brownian motion, that they're just going to be waving around somewhere, and then they have a home position. And then I don't understand why that home position would change if they were not attached. So it just seems to me that the only thing that would change that position is if there was an attachment, because I'm presuming no forces are acting on them other than Brownian motion unless they are attached. So can you just explain to me whether that sort of thinking is right?
Yeah, I would say so. So I cannot say, so it's just what we are measuring. I'm being careful and I'm being extra conservative here. What we are measuring in X-ray is a shift of mass. It's a mass of electrons that are going from one side to the other. So that's why we're interpreting it as, we're saying we see a shift of mass, and we are interpreting it as a change in the proportion of attached cross bridges. But it's exactly as you say. So if they are moving, why they're not moving towards actin? What is causing them to move other than attaching them, they're being attached to actin? So yes, I agree.
I see. Okay, well, I guess related to that, I'm expecting that the cross bridges usually have some home position, a mean, and then probably a you know, a distribution around that, and it's random, which should show up, I presume, as fuzziness in your patterns. And then if they were attached, I would presume that there's less, a more narrow distribution. And I'm wondering, would you expect something sharper in the image, something more regular if they were attached? So then I'm just wondering, something about the fuzziness of the image might be an indicator of attachment.
Mm-hmm. So that's a very good point. So unfortunately, we did not measure the width of the peak of the I11 and IY0 peak. So we did not measure the width. So otherwise I would have had a direct answer to you. But I think that's also a good point. But the idea is that, so we have cross bridges. So the X-ray is not a measurement of one cross bridge. So we have cross bridges along the myosin filaments. And so cross bridges, they might be in different cycle states. So, and what we see is the average of all cross bridges in our sample. So that's why you might still see some fuzziness, what you're calling, because it's the average of many cross bridges. It's not just one that, oh, it's attached, so it's not having, it's a Brownian motion, but at rest it's having the Brownian motion. But it's, yeah, the variability comes from having this as an average of all cross bridges in our section.
Right.
Which might be in different attachment states.
Right. Yeah, I would still guess that you have one part that's deterministic, which is the cross bridge when it's doing its rotation, and then when it's not attached, it's stochastic. And so I wonder if there is something in the fuzziness that would make a difference. Okay, so now let me go to my real question, which was this talk was in a different direction than I expected, because I thought, oh, maybe we'll finally get down to this Titan issue. And then I was surprised that you were talking all about cross bridges. And so I'm just wondering, is Titan for a different talk, or are you willing to share your opinion on where Titan sits in this story?
Okay, so Titan in X-rays, we do not see Titan. Or if we see it, we see the Titan located in the A band, which is attached to the myosin, because the X-ray reflections are from the A band region. And usually when titin is attaching to actin, it's rather in the I band region. So we're coming to titin because we want to exclude the cross bridges to say what is left is titin, especially in the force enhanced state.
I see. Okay, so given that, are you happy? Because it seems like you have some results that are good at excluding cross bridges, but then some are still somewhat consistent. But to me, it's not that clear.
Yeah. So for the force depression, it seems that cross bridges, they play a major role. For force enhancement, and I think when I was talking, I was like confused by my other results about the conformation of cross bridges. So we have some meridional data that shows that the conformation of cross bridges is changing after active stretch, but it's not by the big amount, or it's just by the dispersion of cross bridges more than a change of conformation of cross bridges, which might indicate that it is a titin, like titin plays a major role in the force enhanced state.
Great, thanks.
But in the force depression, it may not play that big of a role.
I see, Doc Syme, you also have a question for Venus.
Hi, Venus. That was a great talk, and thank you very much for the very useful summary of X-ray diffraction and how we interpret it. That was very helpful. So my question has to deal with the mechanism and the mechanism that you were talking about in force depression, with the notion that there could be strain on the thin filaments, that new part of the thin filament that is coming into interactions with the thick filament, and somehow that might inhibit cross-bridge formation. Is there any thought or discussion, I'm not terribly familiar with that literature, is there any discussion about the converse, that you also have strain on the thick filament, and you're now overlapping thin filaments with a region of the thick filament that is under strain, more strain than it was in the relaxed state, and whether that might somehow interfere with the ability of cross bridges to form? I'm just wondering why are thin filaments included in that discussion, but why would thick filaments, strain on the thick filaments, not also be a possibility?
Okay, so at the time when this theory was suggested, 1979, so the backbone of myosin was thought to be inextensible. So it wasn't until Hugh Huxley later in the 90s and Wakabayashi also in the 90s that suggested the extensibility of the filament, especially of the myosin filament, actin as well. So even actin was thought to be inextensible as well, but Maréchal and Plagge still suggested that actin would be strained.
Right.
Why they selected actin and not myosin? Maybe because of the size. So the myosin is a big bone, like it is 15 micrometer, while actin is much smaller, it's 5. So it could be by the same force, it could be strained more.
Yeah.
But I totally agree with you. And there is more thoughts now that the myosin filaments are being strained by active force and by passive force. That's the work by Granzier. They showed that the passive element, just stretching, it would change the conformation of the myosin filaments as well. And this might change the conformation of cross bridges and their ability to attach. So I fully agree with you.
Yeah, I mean, we know nothing, everything is extensible. Yeah. Diamonds are extensible to some extent. And it's those things that are less extensible that are potentially more prone to the effects of strain on them. The thing, you take a dinner plate and you whack it against something, it's not very extensible, it doesn't survive that. And so, I would wonder whether things that are considered less extensible might be even more subject to the effects of strain and how that might impact their function. Okay, thank you.
Absolutely, yes.
I see Yingzhu, you have a question for Venus?
Yeah, very interesting topic, and thank you. I have two quick questions. So first one is, so for the X-ray diffraction to work, the sample has to be crystallized. I'm just wondering, how did you crystallize your muscle sample? And is that your crystallized sample muscle while it's shortening or while it's stretching? And so the second question, what's the energy you're using for the X-ray and why you choose that energy? Thank you.
Yes. So the sample is not crystallized. So that's the advantage of these experiments, is that I know that when people think X-ray, X-rays and think structure, ultra and nanostructure, they think right away crystals and this method. But no, the advantage of these experiments and this type of X-ray is that it allows us to image the muscle while it's activating, it's stretching, and when it's at rest, when it's in solution in physiological conditions. So it's not crystallized. So the other thing, the energy. So the energy, I did not select the energy, I select the beam line. So the beam line, I know that this specific beam line allows for the imaging of the muscle at this level, the cross bridges, lattice spacing, etc. So what's the energy? I think it's between 1 and 12 kilo electron volts. So that's the energy in our bio. I'm not sure if you're familiar with these measurements or with these units, but that's the energy of the X-ray beam that we use in the at Argonne. So it seems that this energy is able, or this X-ray beam is able to image the muscle at the level that we want. But why? I don't know. I cannot push my luck with technical aspect of X-ray more than that.
Thank you.
I see, Brent, you have a question for Venus?
I do, yeah, thanks, Venus. I kind of wanted, when it was all said and done, or when it is all said and done, when people finally know the mechanism of force enhancement, force depression, I was kind of hoping that it would be the same mechanism. And so your results kind of suggest that maybe it's not. And so I guess, am I naive in wanting to think that it's a similar mechanism? Is there still a chance, based on your results and your findings, that it is a similar mechanism, like given any limitations that you have, or are you convinced now that these phenomenons are just completely two different things? One might be because of Titan, one might not be, for example.
So I believe that in both force enhancement and force depression, there is an active component and a passive component. But the contribution of the active component to force depression is higher than the contribution of the passive component. In the force enhanced state, I believe that the contribution of the passive component is higher than the contribution of the active component. So I believe that both contribute, like active and passive contribute to force or to the change in force. So why at passive, in the active, so in the force enhanced state, we believe more in Titan? So first, because we have some experimental evidence for that. And second, because it makes sense, like the sarcomeres at a longer length. So we would think that the passive elements that are stretched when the muscle is at longer length, they would contribute more to when I have a short length, with the cross bridges are the main producer of force and of force. So if I'm not sure if this makes sense, but yeah, this is what I feel.
No, I like that. I really like the way that you explained it, where it's, yeah, you've got the active component, you've got the passive component, and then depending on whether it's enhancement or depression, just means that, you know, it's either the active components a little bit more, the passive. So that's easy enough for me to wrap my head around. Thanks.
Okay, thank you.
I see, Rob, do you have a question for Venus?
Yes, I do. Venus, I thought that was a beautiful presentation and a fabulous piece of science. So first of all, I want to congratulate you. I was delighted.
Thank you.
Art Quo's suggestion of a sort of a fuzzy intensity ratio was what I was thinking too, because I was wondering how confident you were that what you are measuring with that is cross bridges being formed. And is it a simple matter of taking the measurement when it's completely passive muscle and comparing it and stable and passive, and then removing all the ATP and having the muscle go into rigor? And so they are now totally stable. And I presume in rigor, they're all attached. They're certainly not detaching. And whether you would get the two extremes and whether in rigor you would lose any fuzziness. So the width of that seems to me an interesting thing to measure. Do you still have the recordings that you can still actually go and look at that fuzziness?
Yes, I can look at the fuzziness still, and I will. But to answer your question, okay. So where were we? Okay, so these were the first experiments that were done by Hugh Huxley. So you know, Hugh Huxley, when he did these experiments, he didn't know about the side pieces, about the myosin heads. So all he had were these X-ray reflections. And so what he saw, so I thought I would ask you this during the presentation, but I thought just to make sure that you're still following, but I delete them at the end. So we have this muscle, it is at rest, and we have this X-ray of a muscle that is activated. And so what he saw was that in the 1-1 plane, there is like a very, and you're right, there is a fuzzy thing here, and because maybe of the Brownian motion of the cross bridges, and this is the 1-0, and then, oh, sorry, there are no cross bridges here. No, sorry, I made a mistake. And so it's just maybe noise or anything. And then when the muscle was activated, so we see that there is an increase in the intensity of this 1-1 reflection. And so, and because of this, he said that the structure of the myosin, there must be some side pieces that are in the muscle when at rest. They are closely attached to myosin, and then they're shifting towards actin, maybe not in so many words and in these precise words, but they are shifting towards actin or towards the other filament when the muscle is activated. So it's a very, very good thought. So thank you very much. And yeah, I'm glad that I could bring this up. Thanks a lot. But for the fuzziness, I'm sure we did look at the sigma of the peak, but we did not see anything or any differences. But I will certainly go back to this data.
Do you have any, at the end of the experiment, did the ATP get depleted, and do you actually have any rigor to see whether you've gone from Huxley's picture, from nothing in the second band or very little to a strong band, and in rigor maybe an even brighter, stronger, narrower band?
Unfortunately not.
And my other question, quickly, what's the time resolution in making these measurements? Is there any I presume there's no chance of doing anything even slightly dynamic. I mean, how long does it take to make a single measurement?
You know, the X-ray shines on the sample for 0.5 seconds, 500 milliseconds. And these are two, so this is for the reference, and the same thing for the active state. So it's about 1 second. And so for the dynamic states, we did some measurements in the dynamic states. but I have not analyzed them yet. We could, like, we can do measurements in the dynamic state. So the time resolution of the system is very high, of the X-ray is very high. But I have not analyzed them. And then Walter have suggested this as well to me.
Thank you. Beautiful work.
Yeah, thanks a lot.
I see, Siska, you have a question for Venus?
Thank you, Venus. I really enjoyed it. That was really interesting. I just have I'm just out of curiosity. I was wondering if, because you're saying you're moving the sample so that the X-ray would not damage it, right? And I was wondering how you know that there is no damage at all. Yeah, sorry, that was my question.
Yeah, so when I think we tried to do experiments, I think it was with Tim, we called them the death experiments, the death of the filaments experiments, or of the fiber experiments. And so instead of exposing the fiber for 0.5 seconds, we exposed it for, I think it was 2 seconds, just in the same test. And what we saw, you see it very clearly, like after the X-ray, that the force is going down. However, in our experiments, we did not see in any of the fibers like the force is going down after the X-ray. And what we made sure to do was that the size of our filaments, so it's not fibers, so the size of our samples was big, really big enough, like about 300, 400 micrometer, the bundle that was tested in these experiments. So I would say, looking at the force, we did not see a decrease in force after the X-ray, and we had a positive control in which we saw a quick, like, instantaneous decrease in force after the X-ray.
Thank you.
Welcome.
I see, Walter, you have a question for Venus?
Yeah, thanks again, Venus. That was great. I enjoyed that, obviously. Just a few maybe comments to some of the questions that were brought up, regarding, where are the cross pitches, and are they attached and are they not attached, and what would happen, and are they moving around in Brownian motion? And I think we have to be a little bit careful there, because obviously cross bridges, when they are not attached to the actin filaments, when they don't form cross bridges between actin and myosin, we know now that some of them float around, essentially freely, we think, due to Brownian motion. But then there also appear to be what Roger Cook suggests, that there are super relaxed cross bridges that are bound to the backbone of the myosin filament. So not all bound cross pitches would be floating around freely according to Brownian motion. And I think the other thing to consider there is as well that cross pitches can be in different configuration in the attached and detached state, where the mass would be shifting, where the head of the cross pitch is in different positions in the non-attached situation, depending on whether or not the ATP hydrolysis has occurred or not, or in the attached situation, whether or not phosphate release has occurred or not. So that would also cause slight mass shifts. And then last but not least, how strong would the signal be when cross pitches are attached and they have a full activation? I mean, there's very different records of how many cross bridges and what the proportion of cross bridges that are attached in a fully isometric contraction is. And, you can read anything from about 5% to 75%, but I think the consensus is that never really more, even in a fully activated muscle, more than about 25% of the cross bridges are attached at any given time, because the duty ratio is relatively small. And therefore, at any given time, you would expect that at least 75% of the cross pitches, or probably even more, are actually not attached. And so that of course would give you some of the fuzziness of the signal. The second point that I wanted to make regarding the idea about stretching of myosin and whether or not that might explain some of the inhibition. And so The problem is when people think about stretching of myosin with high forces, that seems to activate cross bridges and wake up the super relaxed cross bridges. So, and that would go exactly in the opposite direction of force depression, because when we have high forces during shortening, we get a lot of force depression. So we lose a lot of force. Whereas the theory would say if you have a lot of stress on the myosin, you would wake up a lot of the cross bridges, and people have shown that cross bridge interactions are much more ready in a highly strained myosin. So it kind of, it's a good idea, I think, that Doug brought up, but I think it goes in the wrong direction. Unfortunately, it would be a nice thing though. And there was another comment that I wanted to make, just yeah, but no, I forgot the other comment. But the question that I have, Venus, you know, I've never really thought about it, but the force enhancement and force depression that you're getting is quite big for the relatively small stretches that you make, you know, in the 35 and 40%. Do you have an explanation for that? Because the stretches are from 2.6 to 3, and then from 3 to 2.6, and that's really a lot of enhancement and depression compared to what we normally see. Can you think of anything why that would be?
So for force depression, we usually get like high force depression amounts, maybe not as much as 40 and 35, you're right, maybe around 20, 25. Force enhancement, we do not get as much. And I have an explanation. It's, you know, we usually do the force enhanced state after the reference. But in these experiments, we did not venture to do that because we thought we cannot afford to not seeing force enhancement. Yeah. Because if we do not see force enhancement and we have a limited amount of time, the experiments, like the experiment would be excluded. And so we could not afford that. So what we did the active stretch first and then the reference. And so while
there might be a little bit,
I do the opposite.
So there might be a little bit loss of force that kind of overestimates the force enhancement.
Exactly, that it overestimates the force enhancement.
Okay,
yes.
Yeah. The other thing is, you know, when you talked about the lattice spacing and some of the other measures, you're giving it to a second digit of a nanometer. So you give it kind of a tenth of an angstrom. My understanding was that X-ray diffraction gave you a resolution in the angstrom range, so tenths of a nanometer. Is that correct, or am I off there? Can you be confident in a hundredths of a nanometer?
I thought so, okay. But I need to check this again because I checked the resolution before, and yeah, it seems to me like it's possible, like to go to tenth of an angstrom, but I need to check this again.
Yeah. I'm just thinking of the Raymond papers.
I have doubts now.
Yeah, I'm thinking about the Raymond papers and a couple of other ones, you know, and they usually say that they are in the angstrom, in the tenths of nanometer range, but not in the hundredths of nanometer range. But nevertheless, you know, for the lattice spacing, you are actually off by, you know, about 0.1 nanometer, and so you would see that, and yeah.
And also this depends on the length, on the distance between the X-ray and the detector. And so people are able to detect actin, which is in the order of 2.9 or 3 nanometer, and detect differences there. So I would say, yeah, for the lattice spacing, it's possible to go down to the tenth of the angstrom, especially with detector of 3 and even longer. So I know that for later experiments, we did for like longer detectors when we did the actin.
Yeah. I like the analogy of Dr. Syme, you know, that when things are not very extensible, maybe a small extension might make a big difference, because intuitively, I never could really wrap my head around the idea that the elongation of actin would play a role in how fast or how readily cross bridges attach, because we know that, you know, maximally you get about a 0.5% elongation. So your 1,000 nanometer, actin would go to about 1,005 nanometers, and that tiny elongation would throw the system off, that you lose 40% force. That always kind of struck me as not very appealing intuitively, but it's purely intuition. I think we need to look at that much more carefully, because I think there might be something there where people for many years now have thought along one kind of theory that I really have kind of a hard time accepting, but who knows, you know, it might very well be. And then just a very last comment. In your introduction, you mentioned Rosalind Franklin having given her beautiful pictures of DNA to Watson and Crick. And of course, she has not given them to them. They were stolen from her by Maurice Wilkins, who then got the Nobel Prize with Watson and Crick without the knowledge of Rosalind Franklin. And that fact seems to be fairly well established. So, which of course is the biggest tragedy ever in science, as far as I'm concerned. But she did not give them. They were her pictures, but her Maurice Wilkins got them. And so I always recommend, if you never ever read a book on science, read The Double Helix by James Watson, and who won the Nobel Prize. And he is actually very open about it, that they kind of just stole it from her, and you know, and then they got the results. Anyway, interesting book.
Yeah. I totally agree with this. And you know, I think I'm not sure now when, like, under stress, what I said, but I was planning on saying they were provided with these pictures. You're right.
Oh yeah, they were provided. Okay, yeah.
Were provided with these pictures.
Yeah. Maybe that's how you said.
Yeah, contributed to their discovery, but yeah, I might have said like she gave them these pictures, but no, that was not correct.
It's recorded, so we can go back and see. But you know, I thought it was said too nicely, and I'm just saying this for people to realize, for students to realize how highly interesting science is, and people will steal things from each other to win Nobel Prizes. So anyway, thanks again for a great talk.
Venus, actually, I got a question via Zoom chat from Dr. Brent Reitery in Germany now. So let me read his question. So Venus, if you have ever implemented different skinning methods to evaluate the influence of skinning preparation on the magnitude of the force enhancement or force depression and differences in lactic spacing.
If I have, no, I have not. However, what I would suggest is going from intact to skinned in the same preparation. Like I think we were discussing this at some point in a group meeting, or so do intact fibers, force enhancement, force depression, do the skinning, and do force enhancement and force depression.
Okay.
Maybe Venus, can I just add something here? You did do some experiments by artificially compressing skin fibers and look at history-dependent effects, and that might also give a little bit insight what happens if you have more or less skinning done, how much you compress it or how much you don't compress it.
Yes, but I don't remember the results.
Me neither, but I know you have done it.
Yeah, I think maybe then we can discuss about this later on once Venus quickly check the data set. Kun, if you have any last quick question for Venus?
Well, yeah, I have a question related to the interaction between Venus and Walter, and I didn't understand one point there. So Walter asked about this magnitude of the force enhancement, and he noted that this is larger than what is usually observed. And then it seemed to me that the consensus was that this is because you first do the stretch experiment and then the control experiment. Okay, and then and apparently normally it is observed that then the force enhancement is lower if you do it the other way around, perhaps due to muscle fatigue. Okay, but if that's the case, then it seems to me that actually all the other experiments are underestimates and not that the experiment of Venus is an overestimate. What are your thoughts on this?
I totally agree. And this is exactly what we do and what we intend to do in every experiment when we do force enhancement is we say we want to underestimate force enhancement instead of overestimate it. So we want to not see it if it's not strong enough, but we don't want to see it in a wrong way when it may not be there.
Okay, so
we
then
want that to work against us, not for us. But in these experiments, we cannot afford that luxury.
You want, if anything, this fatigue to decrease your effect and not increase it. But then it is true that, so I was a bit confused by the formulation that you said that your experiment is an overestimation. I thought like, well, no, if that's true, then all of the other experiments are underestimates. Yeah, okay, clear.
Oh, and I want to give an answer to that too. And my answer is do experiment with a cat soleus muscle that you can activate for 24 hours, once a minute for up to 6 seconds, and you don't get any fatigue. It's the perfect preparation. You don't have to worry about anything like that.
Okay, if there is no further question for Venus, I would like to thank Venus again for giving a nice talk. Next week, we will be hearing from Ruokui Deng, and the title is Statistical Shape Modeling of the Knee, Follow-up Research and Plan of a Mechanical Model of the Knee Joints. I hope you all have a wonderful weekend, and I'll see you all next week.